Okay, hello everybody. We start next section, 3.1, primitives of rational functions. And I'll start this section with one example. That is a little bit unusual. Example 1. And that is, in fact, a theoretical example. So, denote Jn equals to integral dx over x squared plus px plus q power n, where p and q are real, such that okay, what is it, p squared minus 4q should be less than 0. So it means the quadratic polynomial in brackets is irreducible over field of real numbers. So no real roots of the polynomial in denominator. And I'll show how to compute this integral. And in fact, we'll obtain a recurrence formula. So, how to compute Jn? Yeah. How to compute it? Okay, let us use integration by parts. So, as usually for integration by parts, let me recall the formula. We should prepare a table for this integration. And so we should choose what is here is u and what is dv. Of course, dv should be chosen in such a way that you can find easily what is v. So, you choose what is u, what is dv. And your choice should be good in the sense that you can find easily what is v. So, what can we choose as dv? Obviously, if you will try to insert this polynomial into dv, right, then it will be very complicated to find v. In fact, it's equivalent problem to find integral. So, the only choice is dv equals to dx. And then what is u? No other possibilities except for 1 over x squared plus px plus q power n. Okay, if dv equals dx, then v is certainly x, right? And to find du, we should find derivative and multiply by dx. So what is derivative? We have, okay, let me write separately. What is u prime? That is x squared plus px plus q power minus n, and we differentiate it, power minus n here, right? So, by the chain rule, that is, firstly, we should write derivative of a power function So power times the base of exponent in power, which is one less than the original, right? And by the chain rule, we should multiply by x squared plus px prime. So obviously the last is 2x plus p, right? That is 2x plus p. And I can write here what is du minus n times 2x plus p times dx over x squared plus px plus q power n plus 1. Okay, that is du. After that, we can substitute those data into integration by parts formula. So what we have? U times v x over x squared plus px plus q power n, u times v, minus integral v x times du. Du contains minus n is a constant, so I put it outside of the integral, so we have plus n, and after that 2x plus p dx over x squared plus px plus q power n plus 1. So from the first glance, this is not a good expression because of, see, what is our win? Did we win somewhere? It seems no, right? We had power n, now we had even greater power. But look, what we can do. First of all, we can divide the polynomial in numerator, which is a polynomial of degree 2, by the polynomial in brackets. So 2x squared plus px over x squared plus px plus q. What is it? That is obviously 2 plus what remains. Okay. If I put 2 outside, maybe I'll do it in more details. 2 times x squared plus p over 2x over x squared plus px plus q. That is 2 plus, so what remains? 2 times x squared plus px plus q gives that one. And we have pi over 2. It means we should cancel minus pi over p over 2 x and minus okay, maybe I'll do it once again in more details. Let me do it in more details. 2 times x squared plus px plus q, right? So we have 2px. In reality, we have just px, so minus px minus 2q over x squared plus px plus q, and it gives 2 minus px plus 2q over x squared plus px plus q. So if we substitute it into our integral, then we get 2 integrals. The first one, 2n, this 2. So you see, roughly speaking, we cancel 1 multiply x squared plus px plus q here, right? So we have n plus 1 multipliers, right? And we cancel one of them with 2x squared plus px. We obtain 2. So it gives the first term with x squared plus px plus q power n. Second term minus n remains integral px plus 2q over x squared plus px plus q power n plus 1 as we had. So look what we have here, 2x squared plus px. I represent it in that form, right? And after that, here we cancel 1 multiply x squared plus px plus q. And in the second term, nothing can be cancelled, so everything remains. Okay, then continue. So what is that? That integral is precisely what we had, Jn, right? So I write it like that, px plus q power n plus 2njn, and here once again we should try to integrate at least part. Which part can be integrated easily? Look, if we try to substitute, to make a substitution, x squared plus px plus q equals to y, then what is dy? dy equals to 2x plus p times dx, right? So it means that if we would be so lucky to get here precisely that polynomial, right, multiplied by a constant, then we could apply immediately integration by substitution. Of course, in general, this is not the case, but we can represent. So look, we want to receive 2x plus p, but we have a different expression, right? The first difference is here, right? 2, that is what we want, but we have p instead of that. So I will write it like that, minus n integral, let me write it like that, p times, okay, p over 2, right, times 2x plus p. That is what would be nice to have, right? But look what remains, p squared over 2, and we have 2q. So I need to add 2q and to cancel this p squared over 2, right? That is precisely the expression in numerator. Okay? After that, what we have? Let me move here. So the first two terms, I will not touch them. Jn. Now look, for the first, so I can represent here sum of two integrals, right? That one and that one. The first one can be computed with the help of that substitution, right? 2x plus p dx, that is precisely what we have, 2x plus p times dx. So, the first one gives minus n p over 2 integral dy over y power n plus 1. Right? That is the first one. The second one, I'll rewrite minus, let's say, 4q, okay, minus 2m times, not 2m, n over 2 times 4q minus p squared. Constant term outside, and it's nice to recognize immediately that term, right? For sure, that is not 0, right? So, I said, maybe we will be lucky to get a multiplier of this polynomial. For sure not. Right? So, this condition guarantees that we'll be unlucky with this. So, this term is never 0 under our supposition. Okay? So, and what remains? Look, integral dx over that one. And that is precisely that integral, right? But instead of n, now we have n plus 1. So, j n plus 1. Look, let me look at this formula. So, of course, we should also suppose n is natural. And what is the result? The result is not a formula for Jn, but recurrence formula. Not explicit formula, but instead of that we have a recurrence formula. So let me write it down. So I put Jn plus 1 into the left hand side and Jn into the right hand side. So Jn plus 1 equals to, so recurrence formula. Jn plus 1 equals to, okay, I put to the left, divide by this term, so 2 over n 4q minus p squared times x over x squared plus px plus q to the power n plus 2n minus 1 jn. And, okay, that integral y to the power minus n minus 1, the integral gives 1 over this term. So, let me compute it separately, recall. We have n plus 1 is greater or equal than 2, because n is natural, right? So, that is y to the power minus n minus 1, so 1 over minus n times y to the power minus n plus c. So we cancel with this minus n, right? And what remains, let me write it here, plus p over 2 times y to the power n, x squared plus px plus q to the power n. That is the formula. Of course, we can write together those two terms, but it's not so important, right? So shorter formula will be jn plus 1, 2 over n 4q minus p squared times 2x plus p over 2x squared plus px plus q power n plus 2n minus 1 j. That is the recurrence formula for computation of this integral, right? So how it works? You start with j1. Let me compute j1 explicitly. dx over x squared plus px plus q. So what is it? I can rewrite it as dx over x plus p over 2 squared minus p squared over 4 plus q, or integral dx over x plus p over 2 plus 4q minus p squared over 4 square, I forget square, and okay, that is a table integral or table integral with prime, right? If you substitute x plus p over 2 equals to, let's say, w. So x plus p over 2 equals to w. Then we obtain that integral equals to integral dw over w squared plus 4q minus p squared over 4. That is a positive number, right? So we can write it as 1 over, that can be written as square root of 4q minus p squared over 2 squared, so a squared, right? So we have table integral, I don't remember the number, of course, some number with prime, right? When we have a, of course you can take this outside, this term outside, and make a substitution once more, but I'll write the answer 4q minus p squared over 2 times how to write arctan, or let's say arctan, w over square root 4q minus p squared over 2 plus c, or 2 over square root 4q minus p squared arctan x plus p over 2 is w, 2x plus p over square root of 4q minus p squared plus c. So you see, we start with j1, it is written explicitly, right? Then if we want to compute j2, we substitute instead of n equals to 1. It gives j2. Once we have j2, we can compute j3 and so on, right? So in principle, it gives a possibility to write down the answer for arbitrary n, right? But of course, it's not immediate, but in principle, it can be done. Okay, so that is what it was. In fact, it was an example of the most complicated case to find a primitive of rational function. It was the most complicated. Now we can consider the general case, and I need to introduce a definition. So let's start with definition. Definition. A proper rational function is an expression, okay, not expression, a function p of x over q of x, where p and q are real polynomials with degree p strictly less than degree q. So that is a proper rational function. Okay. Now I'll start the general case. Okay, maybe I'll keep for a while that formula, recurrence formula, for another example. I'm not sure if I'll be able to do it today, but so lemma 1. If p of x over q of x is a proper rational function, and a real is such that q of x equals to x minus a power alpha times q1 of x, where q1 of x is a polynomial, is a real polynomial, of course, a real polynomial. q1 of a not equals to 0. I think you know that it can be expressed also by the sentence that a is root of q of not a root, 0 of q of x of multiplicity alpha. Of course, alpha is a natural number. Then there exists real number A such that P of x over Q of x equals to A over x minus A little power alpha plus P1 of x over x minus A power alpha minus 1 Q1 of x, where the second term is a proper rational function. So, what this lemma says? Look, if you have here, roughly speaking, a multiplier of this form, then you can find a constant such that you can separate this multiplier from the other, right? So you see that here you had x minus A power alpha, and after that you have one term which has only x minus A to the power alpha in denominator, right? In other terms you have x minus A in a smaller degree, right? So if you apply it several times, then you will get x minus A power alpha, then x minus A power alpha minus 1, and so on, up to, you see, up to x minus A in denominator, right? So once you have alpha natural, you can diminish this exponent step by step, right? In such a way that finally you get x minus A just that one, and then nothing here, right? No x minus A remains. Okay, proof. So, what we want, in fact. So let me write down what we want to obtain. If you add those two terms, right, it means we need to find a common denominator. And what is common denominator for those two? You should multiply this by x minus A, right? And it gives precisely Q of x. So Q of x is common denominator for those two denominators, right? Q of x. So it means that the desired equality is, so what we want to find, if it's possible to represent P of x as, look, what is it? So what we need here, A times Q1 of x, right, plus x minus A times Q1 of x. That is what we want to obtain, right? How to find capital A from this equality? Just substitute x equals to little a. If you substitute x equals to little a, then what you obtain? P of little a equals to capital A times Q1 of little a, right? It disappears. So it gives capital A equals to P of A over Q1 of A. So now, in fact, we are done. Why? Look. So we know Q1 of little a is not 0. That is by the supposition, right? So that is a well-defined number, right? So we have capital A, and if we substitute this number, then what remains? Look. So we consider now P of x minus P of little a over Q of a times Q1 of x. What is it? That is a polynomial, right? That is a polynomial. Real polynomial. And if you substitute x equals to little a here, then it is equal to 0, right? And hence, by Bézout theorem, it can be written as x minus a times Q1 of x, by Bézout theorem, right? And the theorem is proved up to the last thing which we need to check is that P1 over this function is indeed a proper rational function, but just compare degrees, right? So degree of P1 is for sure less than degree of Q1 and less than degree of P, less than both of them. No, I'm wrong, I'm sorry. Degree of P1 equals to maximum, less than maximum of those degrees, minus 1, right? That is what I can assert for sure. And so degree of P1 is less or equal than maximum of degrees P and degree of Q1. And then, if you look here, what is degree of denominator? Degree of denominator is degree of Q minus 1, right? So, that is strictly less than degree of Q minus 1. Why? Why it is strictly less? Degree of Q1, yeah, is strictly less because of, you need to consider here several cases. Alpha equals to 1, alpha not equals to 1, because yeah, it's different in both cases, but you can check it easily. I will not do it. So, lemma 1 is proved then. Now, lemma 2 is an analog, but for a complex zero. Okay, so lemma 2, if P of x over Q of x is a proper rational function, okay, maybe better here to write like with a 0 z naught equals to x naught plus I y naught not equals to 0 of multiplicity beta natural, then they exist B, C real numbers such that P of x over Q of x equals to bx plus c over x squared plus px plus q power beta plus p1 of x over x squared plus px plus q power beta minus 1 q1 of x, where x squared plus px plus q equals to x minus z naught times x minus z naught conjugate, q of x equals to x squared plus px plus q power beta times q1 of x, and second term in, let me enumerate it by star, in star is a proper rational function. So that is an analog of lemma 1 for complex 0. You see now, if we have a complex 0, right? Not real, complex not real 0. Why not equals to 0? Then we know by one of lemmas of a former section, right, that if you have a real polynomial q of x, and it has a complex 0, z naught, then conjugate z naught bar is also a 0 of this polynomial. That is what we know. If we have a real polynomial, then for sure, together with a complex 0, non-real z naught, it has also 0 z naught conjugate. And if q of x has both zeros z naught and z naught conjugate, right, then by Bezout theorem it can be divided by that product, right? And the product of those two gives, okay, we can write explicitly what are P and Q easily, right? How? Look, x minus z naught, so that is not a proof yet, it's just a discussion. So that is x minus x naught minus I y naught times x minus x naught plus I y naught. Because z naught conjugate, you should change sign here, right? Put minus here. So if you subtract, then we have plus. Then what is it? That is x minus x naught squared minus I squared y naught squared, or x squared minus 2x x naught plus x naught squared plus y naught squared. So you see p equals to minus 2x naught and q equals to x naught squared plus y naught squared. By the way, once again, p squared minus 4q squared, what is it? Here, look, it's 4x naught squared minus 4 times x naught squared plus y naught squared. That is minus 4y naught squared. And since y naught is not 0, then it is negative for sure, right? So this quadratic polynomial is irreducible over real numbers. It has no real roots, real zeros, right? And we have two complex zeros, but they should be conjugated. So, and since we suppose that z naught is a zero of multiplicity beta, it means we have x minus z naught power beta in q of x, right? But since q of x is a real polynomial, then x minus z naught conjugate should be also in power beta. And that is why we can represent q of x in that form. So, oh, maybe I should indicate here q1 of z naught not equals to 0. That should be added. Okay, proof. Now proof. So once again, let me write the desired equality equals to bx plus c. So once again, common denominator is q of x. Hence, bx plus c should be multiplied by q1 of x. And we add p1 of x times x squared plus px plus q. That is what we want to attain. That is our goal. So we need to find b and c such that this equality holds. And once again, the idea is to substitute x equals to what? Zero, right? 0 of the polynomial q. And it means x equals to z naught. Or x naught plus I y naught, right? So what we have, p of x naught plus I y naught equals to b times x naught plus c plus I times b times y naught times q1 of x naught plus I y naught. And x squared plus px plus q equals to 0, right? Because it's that one. If you substitute x equals to z naught, it's 0. Now, look, let me rewrite it in that form. bx naught plus c plus I b y naught equals to p of x naught plus I y naught over q1 of x naught plus I y naught. I can do it because of that supposition. q1 of z naught is not 0. And remember, I want to find b and c are real. So that is a complex number, because you substitute into the real polynomial complex number, right? And now you see, this is real, and this is pure imaginary. Hence, we can compute firstly b. b equals to imaginary part of p x naught plus I y naught over y naught times q1 of x naught plus I y naught. Just take that one, divide by y naught. Y naught is real, of course, not 0. And take imaginary part, and you obtain b. And once you know b, you can find easily c, right? How? You can write an expression explicitly. Real part of, okay, p of x naught plus I y naught over q1 x naught plus I y naught, right, minus b x naught. b is known now, right? b is real. b is real, x naught is real, so c can be written in that form. So we found explicitly formulas how to express b and c in terms of data. P, q1 are data, right? X naught, y naught are data. And okay, after that, so you see, once we have this, the rest is what? The rest is to check that indeed we have this equality, and it can be done absolutely analogous to the proof of lemma 1. So let me write it down. So b and c now are found, right? And we consider the polynomial p of x minus bx plus c times q1 of x. That is a real polynomial. And what we obtain? Because of the definition of b and c, right? That is the definition of b and c, right? How we obtain them? Look, because of that definition, what we observe? We observe that this polynomial, that is a real polynomial, and it has 0 z naught. Once it has 0 z naught, and it is real, it has also a 0 z naught conjugate, hence it can be written by Bézout theorem as x squared plus px plus q times a polynomial p1 of degree. What is about degree? Degree of p1 is less or equal than maximum of degree of p, degree of q1 plus 1, and minus 2. That is an estimate for degree of p1. And you can again check that indeed it gives you that the second term is a proper rational function. Okay, now lemma 2 is proved, and we can find not find, we can prove the main theorem of this section, which gives also an algorithm to compute integrals of rational functions. So, theorem. There is only one theorem here in that section. For an arbitrary real rational function p of x over q of x there exists a primitive which can be expressed with the help of elementary functions. So, in fact, that is the only unique class of elementary functions which have for sure a primitive expressed in elementary functions again. What are elementary functions? These are all functions which we considered before. I mean, trigonometric functions, exponential, power function, inverse trigonometric, inverse, hyperbolic, and so on, so on. So, all functions which we considered are called elementary. And, in fact, no other class, I mean, if you will try to expand a little bit, then there are very simple functions which has no such primitive. For example, this function sin x over x has no primitive which can be expressed in terms of elementary functions. No. There is sometimes it is called a special function, integral sign. But one of those primitives is called integral sign, denoted by that, and so on. So there are many functions, I mean very simple functions, right? But you cannot find a primitive in terms of elementary functions. So practically the only huge class which has that property is the class of rational functions. So proof. If p of x over q of x is not a proper, i.e. degree of p greater or equal than degree of q, right? Then by lemma 1 of section, oops, I don't remember, I think it was section 2.2, last section of the former lecture, because there were two sections, I think, 2.1 and 2.2, right? Lemma 1 said that if you have degree of P greater or equal than degree of Q, then you can divide P over Q. So P of X equals to M of X times Q of X plus R of X, where M, R are polynomials, real polynomials. Degree of M equals to degree of P minus degree of Q, and degree of R is strictly less than degree of Q. So once you have it, you can write indefinite integral P of X over Q of X dx equals to integral M of X dx plus integral R of X over Q of X dx. Now you see that is proper. And what is here? Integral of a polynomial. Integral of a polynomial is a polynomial again, right? Because integral of x to the power m dx is equal to x to the power m plus 1 over m plus 1 plus c, where m, 0, 1, and so on, for sure, right? Because the only exclusion is when m equals to minus 1, and we don't consider it when we have a polynomial here, right? So it means that we can consider only proper functions, right? So now we can consider only proper functions. Then what happens? Look, by main theorem of former section, by theorem 2, I guess, of section 2.2, I hope it's correct. I don't remember precise. Can you have you lecture notes of former theorem? Not theorem 2. It was corollary. Sorry. It was corollary. Yeah, it was a corollary. Oops. I am sorry. I forget. From the beginning. Today's section 4.1. I'm very sorry. Yeah. So here 3.1. I forget about numbers. I am very sorry. Yeah, that is by corollary. Corollary to theorem 3.1. Yeah. Corollary. from theorem 2 of section 3.1. We can write q of x as a product, okay, constant times x minus a1 power alpha 1 and so on, x minus a r power alpha r times x squared plus q1x plus q1 power beta 1, so on, x squared plus ps x plus qs power beta s, where all a1 so on ar p1 so on ps q1 so on qs are real, alpha 1 so on alpha r beta 1 so on beta s are natural, and r is rs are natural or 0. So, and what we have, the sum of alphas plus 2 times sum of betas equals to degree of the polynomial q. Degree of the polynomial q. C is the leading coefficient of q. That is by corollary. I didn't write in the corollary this equality, but it can be obtained easily looking at leading powers. Now, look. Now we can apply lemmas 1 and 2 of today's section. Yeah. Today's 4th section, yes. I made a mistake in number of lecture. Okay, so how we apply lemmas? Look, we start with, I look at r of x over q of x. We start with a1. Here we have power alpha 1, right? So we know by lemma 1 it has the following representation. A1, let's say 1 alpha 1. Alpha 1 plus r1 of x over x minus a1 alpha 1 minus 1 q1 of x. That is by lemma 1, right? After that, look at this. That is again a proper rational function, right? Degree of numerator less than degree of denominator. And we can apply once again lemma 1, right? What it gives? It gives a1 alpha 1 over x minus a1 alpha 1 plus a1 alpha 1 minus 1 x minus a1 power alpha 1 minus 1 plus, let's say, r2 over x minus a1 power alpha 1 minus 2 q2 of x, right? And we can continue on and on up to which moment? When we should stop? While here it's 0, right? And when it is 0, that is 0 when the last exponent is 1, right? So it means that after many applications of the first lemma, we obtain r of x over q of x equals to sum, okay, let me firstly I from 1 to r, sum, j is here, let it be k from 1 up to alpha I, and coefficients are a, I, k over x minus a, I is number of the 0, and power is k. Look, so you see, I demonstrated what is going on for one real 0, right? For one real 0, you apply several times, and every time the degree of denominator will be smaller and smaller, right? So, firstly, we consider in such a way all terms with x minus a1, right? After that, we'll start to consider all terms with x minus a2, and so on, so on, so on. Finally, we'll get such an expression. Plus, let's say, r tilde of x over q tilde of x, where what is q tilde? Q tilde is precisely the product of all complex zeros. So, we considered all terms with real zeros firstly, and collect them together. That is collection. Look, here are just two of them, right? And then we continue. It gives you one term for that sum, I equals to 1, right? 0 equals to 1. A1, sorry, number of 0 is 1. A1 first. After that, you continue with other zeros, and you obtain this expression. After that, we work with second lemma, right? How we work? We know r tilde of x over q tilde of x equals to b, okay, let it be 1 beta 1 x plus c 1 beta 1 over x squared plus p1 x plus q1 power beta 1 plus r tilde 1 of x over x squared plus p1 of x plus q1 power b to 1 minus 1 q tilde 1 of x. That is application of lemma 2, right? We have one term in maximal power, right, here in denominator, and a linear polynomial in numerator. Then once again we continue like here, right? And we continue up to disappearing of this term, right? So it means that at the very end we obtain the representation which is called partial fraction decomposition. So, partial fraction decomposition. Fractions decomposition. That is, for a proper rational function can be written as that sum of terms aik over x minus ai k plus sum j from 1 to s, sum l from 1 up to beta j, b j l x plus c j l over x squared plus pj x plus qj power l. That is partial fraction decomposition. Of course, what happens if r or s equals to 0? Because some of them can be 0, right? Then what happens if, let's say, r equals to 0? No first sum, right? R equals to 0 means that our polynomial has no real zero. That's all. And after that, what happens with integral? Look, we need to compute integrals of the following form. For example, that one, how to compute it? What we obtain? If k not equals to 1, then that is power function, right? If k equals to 1, then that is logarithm, right? So in any case, it can be written with the help of elementary functions, right? Now, what is about integrals bx plus c over x squared plus px plus q power beta dx? That can be computed in a similar manner with the example, right? So we try to make a substitution, x squared plus px plus q, right? We represent numerator as bx plus c equals to b over 2 times 2x plus p plus what remains, The first term gives you dy over y power beta, and gives either power function of y or logarithmic function of y. And the last term, recurrence formula. Recurrence formula gives an expression in terms of, so you see, either rational functions or what was J1? J1 was arctan, right? So in fact we can say more precisely which elementary function can be involved. Arctan, logarithm, and power function. Nothing more, right? Every integral of real rational function can be written with the help of those elementary functions. Logarithmic, arctan, and power. Nothing else. That's all. Thanks for your attention.